are you, everyone? Good. I didn't have your exam. I didn't done grading them. In fact, I didn't even start grading them. I was trying, but I had my own homework, which I had to submit really urgently. So it took all of my time. So most likely I will be able to finish by Wednesday. If I cannot, then I will give you exam back on next Wednesday. This Thursday we're supposed to have a class, but I sent you an email. Did you read that? That I have my own class on Thursday, my 2 classes, so I cannot actually hold Thursday's classes. So we'll have an off day. And next Monday, I told you that we will be online for 1 hour. But then I was thinking, well, instead of just being online for 1 hour, I can just make a recording for 1 hour and then you can watch on your own time. Okay. So whatever we finish after Wednesday, on the new materials, I'm going to make 1 hour recording and then you can just watch the recording. Or maybe I can make 2 hours recording since it's online anyway.
Hello?
1 second, Musfika. What, Jocelyn? Yeah, we are supposed to because Thursday they are making Wednesday schedule this week. But Thursday I have my own classes which I didn't realize before. So if I be here or teach you online, then I have to skip my own classes. But my own classes held only once a week. So I was thinking, well, we already have 2 classes here this week. Then we can skip the third one and we can go on next week. So it will not going to affect us much. Yeah, Musfika, go ahead.
No, I just wanted to say that I'm sorry. I saw your email about coming in person, but I already told you I couldn't because of Ramadan.
I understand, no problem.
Okay, thank you.
Okay, so any question before we start? Any comments, concerns? Yeah, once I'm done grading, like if I done grading by Wednesday, I'm going to give you the exam in person Wednesday. But if I'm not done grading them, then whenever I'm done grading, I'm going to put the grade on Brightspace and then email you. Well, I'm done grading your exam. You can check your score. Any other question? So I was supposed to start our derivative with this section, but I skipped it because usually we don't use the definition of the derivative to find the derivative. So I was thinking, well, let me just teach you shortcuts and then I'll tell you the details, which was kind of bad idea because I could see that you guys had no idea what is derivative, right? And then you just memorize all those formulas instead of understanding them. So on your reflection questions, most of you said, well, going over in details about the scenario behind the materials will be helpful for you. So this is the details behind derivative, where the derivative come from. So previously, in chapter 1, we seen, or I don't remember, did you see it here or not, that we have 4 types of slope: positive slope, negative slope, zero slope, undefined slope, right? Based on 4 types of line. So if you have a line that is going upward or increasing, we have a positive slope. So when you walk from your left side to your right side, from your left side to your right side, if you walk upward, we have a positive slope. If you walk from left side to right side, if you walk downward, then we have a negative slope. And then if you walk on a straight line, we have a zero slope, like horizontal line. And when you walk straight up and down, you don't go left to right, you only go straight up and straight down. That time we don't have a slope, because in order to have a slope, we have to walk from left to the right. But in a vertical line, you don't walk from left to right, you walk straight up and down. So 4 types of slope. And we can find the slope based on 2 points, any 2 points, right? So if you have any 2 points, then our slope is y2 minus y1 over x2 minus x1. Okay, so that slope concept comes in derivative. What is derivative? It's the slope of the tangent line that goes through a curve. So when you have a line, every 2 points have the same distance. For example, the distance between here and here, not distance, the slope between these 2 points is the same slope between these two. It's the same slope between a point here and a point there. So it doesn't matter what 2 points you take, every 2 points has the same slope. So this is a good thing about a line. The slope never changes. The slope tells us about the straight line is always same for any 2 points. But look at a curve. A curve is not straight. Sometimes it goes up, sometimes it goes down, sometimes it slide down, sometimes it go upward. The curve has so many fancy things, right? It's not straight. So finding the slope of a curve is kind of impossible because every 2 points has a different slope. For example, the slope between these two is positive if you draw a line, but the slope between these 2 points is negative if you draw a line. See, same curve, they have different slope. Also, if you want to find a slope here, it's a straight line, the slope is 0. And if you want to find a slope here, it's a straight line, the slope is undefined. So a curve has all these slopes. That's why we cannot find the slope between any 2 points. So what we do is that we take 2 points, any 2 points, and then we take the limit of the 2 points. What does that mean? It means we make the 2 points closer and closer and closer and closer to one another. And we find the slope of a point, not slope of a line. So what's the slope at a point? Okay. At a point on the graph that goes through at a certain point. So we cannot find a slope of a piece. We can find the slope at a particular point. That's the derivative. What's the slope at a particular point? So we say, well, slope of a particular point is same as is the slope of the tangent line that goes through that point. For example, here, if you want to find what's the slope at this point, we can find the slope at that point. This point will have a different slope than the slope at that point. So every point has a different number for their slope. So what we do is, well, in order to find slope at any point, do we have any method that we can find, that we can use to get the number for the slope for any point on the curve? Mathematician says, well, it is possible. All you have to do is find a formula for your slope. If you can find a formula for your slope, then depending on where you x value use, you can just substitute x and you find the y value, which is the slope at that point. That formula is a derivative. Is it clear now? It's a derivative is the slope at a point, at one point only on a curve. And that point, we said, well, that point, if you draw a line, that line is called tangent line. Anytime you see the word tangent, it means it's touching the graph only at one point. So derivative is the slope at one point of the curve, which is the same slope that goes to that point, which is the same slope of the line that goes to that point. And that line is called tangent line. So derivative is the slope of the tangent line, is the slope at one point of anywhere in the curve. Now, how do you derive that? So the definition of the derivative comes from the slope formula, y2 minus y1 over x2 minus x1. This is true for any 2 points. But we are finding the slope at one point. So at that one point, our slope is 0 over 0, which is undefined, right? Because the 2 points we are plugging here in the formula, it's the same point, so the result will be 0 on the top, 0 on the bottom. So what we do, instead of using the formula directly, we use the difference quotient. Did you ever see the difference quotient formula? You did? No? So difference quotient is same as the slope formula. They look different, but actually they are same. How they are same? Let's say we have 2 points. One point is C, x equal to C, and another is little bit right on the C. So C plus some distance h. Okay. So this C has a y value f of C, and C plus h has a y value f of C plus h. So if you want to see what is the slope of the line that goes through these 2 points, then you can find them easily. It's y2 minus y1 over x2 minus x1. So this is our y2, this is our y1, this is our x2, this is our x1. So you plug into the slope formula and then observe point reference. On the top, we have nothing to do because these are 2 different y values. But on the bottom, when you take out your parentheses, you get c plus h minus h and h cancel out. It is c. Sorry, moment. It's a c. No. C plus h minus c, my bad. So, hypo. So c plus h is our x2, c is our x1. So c and c cancel out, we get h. So this is true for any x value. So we have x plus h minus f of x over h. What is that h? That h is the distance between the two x values. Whatever you have here, from here to here, this is the distance h. Now, that slope is actually not the slope of the tangent line, it's the slope of the secant line. What is secant line? Secant line is any line that uses 2 points from the graph, from the function. Okay? So what you do, in order to find the slope of the tangent line, we take the slope of the secant line. It means we take any 2 points and we see what's the slope of the line that goes to the 2 points. And then we eventually make the distance between the 2 points smaller and smaller and smaller. So that eventually the 2 points turn into 1 point. And that 1 point gives us the slope of the tangent line. Okay, so let me show you the details, what I was saying. So right now our C is here, C plus H is here. Next, we bring the C plus H closer to the C. So let's say we take a point here, and then we see what's the slope of that point. And then we make this point closer, even closer to the C. So let me change the color. Let's say we bring it here. And then we see what's the slope between these 2 points. So eventually we make the right point closer and closer and closer and closer, closer to C. And then the 2 points become 1 point, merge into 1 point, and gives us one number, or gives us the slope. So that work, what you're doing, like we are moving our point, the right point, closer and closer to the left, it's the same as we are putting a limit into our distance between the 2 points. So first we had C here, C plus H there. Now it says H is going towards 0. It means the distance between the 2 points are getting closer and closer and closer and closer and closer. Eventually the distance between the 2 points is nothing, it's 0. They're same points. So we can apply the limit here because limit always exists. Okay, one-sided limit always exists. So when you do that, we'll have some type of limit. If you look at one side, either from the left side or from the right side, you'll have some type of limit. So we bring this distance between the two extremes closer and closer, and then whatever we left with, that's the slope. So this is the definition. So that definition right here, that's the definition. So that is the slope of secant line. But when you put the limit, it means you are making your distance smaller and smaller and smaller, and the secant line becomes tangent. So that's why tangent line. The result of this limit is the slope of the tangent line. And that is the derivative. I will. I didn't so far. Okay, so why we are applying limit? Why don't we simply say h is 0? Well, if you put h is 0, then we have 0 over 0, everything becomes undefined. Or you have something over 0, something becomes undefined. So we cannot just substitute h is 0. What we can do is we can bring h from a big number to closer to 0, but we can never substitute h is 0. Okay? That's why when we have this type of problem, remember I said we have to modify our function first. So that when you plug your limit into the function, you don't get something undefined. So here, if you plug h equals 0, it's undefined. It doesn't exist. So we are applying the limit and see what happens. So we modify our function based on whatever function we have from the curve. Okay, so the formal definition of the derivative is limit h is going to 0 of your difference quotient. This formula is called difference quotient. When you apply the limit of difference quotient, it becomes the derivative of x. It means you can find the slope at any x value using this formula. The second definition is, well, if you want to find the derivative at a certain point A, okay, one point A, then you can write this as the limit x is going to A, that number of f of x minus f of a, where x minus a. So this is your y value, y2 over y2 minus y1, x2 minus x1. And you're applying your limit on A. X is going toward A. They are both same definition. One is when you know your point. Well, I want to find the derivative of this graph when x is 5. When you know your point, you can use this definition. And when you want to find a general formula for derivative at any point in the curve, then that's the general formula. Now, how do you use them? Oh, before even doing that, the notation I didn't tell you before, which I should have, is that f prime of x, we say f prime of x, it means derivative of f at x. dy dx means the same thing, we call them dy dx. It means derivative of y respect to x. Y prime of x, we call y prime of x, is same thing as derivative of y in terms of x or respect to x. Or we can write d dx of f of x is the derivative of f of x. So this is the notation and this is how you say them. And this is a derivative at a certain point A. So f prime of A, y prime of A, dy dx for x equals A, or derivative of f of x for x equals A. So all these things means you're finding the derivative of y or derivative of x respect to x. So an independent variable is x, and whatever we have on the left side is a dependent variable. Based on that, we can say that means if you have dx over dt, this is same as you're finding the derivative of the function x respect to t. If you see dy over dt, it means derivative of the function y respect to t. If you see dz dt, it's the same thing. It's a derivative of the function z respect to t. So whatever is on the top, that is your function, and whatever is on the bottom, that's an independent variable. Okay? So for example, you may have a function, example, x equals t squared plus t. So when you take the derivative, you write dx dt on the left side, and you take the derivative, t squared is 2t. So let me write it down. So dx dt is 2t plus 1. Okay? And dy dt, so let's say you have something like y equals 2t plus 1. Then in this case, if you're finding the derivative, it will be dy in terms of t, so it's respect to t, and you simply take the derivative on the other side with t. Same thing z, let's say you have a function z. Let's say this time I'm giving you something different. This, never mind. This is implicit differentiation. So z, let's say have 5t cubed. Then your dz dt is 15t squared. Okay. Any questions so far? Now, one example when actually we use the definition or how to use definition. You can use a definition for any case, okay? But we don't because it takes longer time to calculate the derivative. This is some example where we apply the derivative, so some application of derivative. We use it many places. For example, rate of change of quantity or increasing, decreasing function, tangent line of a car, maximum, minimum value, linear approximation. In all these concepts, we use derivative. So some of these we are going to do in related rate problem. So here, it says find the derivative or differentiate. All of these are same thing. Differentiate means take the derivative. Find the derivative means you're finding the derivative. Find the slope of a curve, it means derivative. Find the slope of the tangent line means derivative. So if you see any one of all of these, it means they are simply telling you that, hey, find the derivative. Okay. So it says find the derivative using definition. Now, they didn't tell us to find the derivative at a certain point. That means we are going to use the top definition with h on the bottom. So definition is limit, oh, before even that, derivative of f for any x value is the limit h goes to 0, f of x plus h minus f of x divided by h. So how to use it? From here, you find what is f of x plus h. And then you substitute this f of x from that quantity. So f of, let me do it on this side. F of x is negative 6x squared plus 4. So f of x plus h is negative 6 parenthesis square, inside which you place x plus h instead of a simple x. And then you simplify. So to simplify, do you do multiplication first or do you apply the power first? Power. So can you just distribute the power? No, we cannot use this. We cannot do the distribution because distribution of power works only in the multiplication and division. For example, if we have xy squared, then yes, we can distribute. It becomes x squared y squared. Or if you have x over y squared, then it becomes x squared over y squared. So only on multiply or divide, you multiply or divide, then you can distribute the power. But for addition subtraction, you can never distribute. Instead, you use FOIL to multiply it twice, or you can use the special formula. So if you do use a special formula, it says take the first quantity, square that, and then add 2 times their product. And lastly, always add the second quantity square. If you have no idea what I'm doing, so this is same as you are multiplying this twice. So you FOIL them out and multiply, you get the same result. We still have our plus 4, which we did not use, so bring it down. And then we distribute the negative 6. So we get negative 6 x squared minus 12 xh minus 6h squared, and then our extra 4. And they have nothing in common, so we just keep them. So you go back here, and we substitute everything here. Limit h goes to 0. Now this thing is this entire thing here. So we are going to write this entire thing here. Negative 6x squared minus 12xh minus 6h squared plus 4. And you're subtracting f of x. So f of x is same as this thing. So you substitute within a parenthesis, because anytime you subtract, the sign will change. So it's negative 6x squared plus 4. But because of this negative, this will turn into positive, and this will turn into negative. So we get limit h goes to 0, negative 6x squared minus 12xh minus 6h squared plus 4. And then we change the sign. So plus 6x squared and minus 4. Whole thing over h. What do you notice? Positive 6x squared and negative 6 squared cancel out. Positive 4, negative 4 cancel out. And the leftover two terms, they both have h in them, right? So you can pull out h as a common factor. So we get limit h goes to 0. And if you pull out an h, you get negative 12xh minus 6h. Sorry, no more h. Over h cancel out. You have limit h goes to 0. I forgot my negative. Negative 12x minus 6h. Now you can substitute h with 0, because this time it is not going to give us anything undefined. So when you substitute this equals 0, we simply left with negative 12x. And that's the derivative of f of x, which we already know, right? Using our power formula. So the shortcut we learned, we know that f of x, 6x squared plus 4, of course, its derivative will be negative 12x plus 0, which is negative 12x. So using the shortcut, we can find the derivative, and they're telling us, well, if you don't know your shortcut, how can you find it? That's the formal method. And that's why I didn't teach you, because you're not going to use it anyway, right? If I tell you to find the derivative, will you ever use the definition? Never. Or you can use the definition for any type of function. The difference will be how you modify in the middle. So here we modified by distributing by using FOIL, multiplying that. But if you have a square root, you do conjugation. Other instructors do. I don't. I hate them. But if you want to use it, feel free. You can always use a definition. No problem. Any question? Any other question? No? Okay, then. I have 3 examples. These are kind of related with the definition of the derivative. So the first one is saying what's the derivative when derivative at 0? Well, you cannot find it directly because this is a piecewise function. When x is not 0, it's x squared sine 1 over x. And when the x is 0, y is 0. So you have to use some type of trick to know what's the derivative when x is 0. And then we have two other examples. The top one is asking, well, and you have another piecewise function, and then you have two choices. At 3, the limit exists. At 3, the function is continuous. At 3, the function is differentiable. Which of these three are correct? So these are options. Either only one correct, or 1 and 2 correct, or 1 and 3 correct, or all of these are correct. Find out what's the answer. Which one of these is correct? And the last one is saying, well, if a function has a derivative at 5 is this, then what is that function? Okay. So 3 examples, try with your group, and it's a prayer time. Let me pray, and then we'll do them together. Ellen, we have some interesting question. If you want to try them. I guess done? No. Did you understand the first one? No. How about the second one? You're okay with the second one? And the last one? Good? Oh, so the last one, the second was easier than the first one. I'll take a few more minutes. Let me call your attendance. I'll do them. Kimberly? Here. Carrie? Here. Judith? Absent. Mac? Ziad? Chi? Chi? Jocelyn? Yeah. Lucas? Restaurant? Boy? Logan? Ellen? Here. Musfika online, right?
Yes.
Nick, Sanzim, Shian, no laptop in the class. Close it. Raka here, Ella here, Apollo here, Andy. Andy, you didn't send me your reflection. Make sure you do it tonight. Okay, so I gave you the hint for the first question. I said use the definition for the derivative at a point, and also use a squeeze theorem. Do you remember your squeeze theorem we went over in one of the class? You don't have to apply it. Okay, so hint number 1. It says use the definition, the second definition. This is what it means. The second definition is limit x is going to a f of x minus f of a over x minus a. This is the definition when you know where you're finding your definition. I mean, where you're finding your derivative. So in our case, we have limit x is going to which number? What is our limiting point here? 0. So it says find derivative at 0. So this is derivative at a, and we are finding derivative at 0. So derivative at 0 is limit x is going to 0 of f of x minus f of a divided by x minus 0. Sorry, f of a is f of 0. And you already know what is f of 0, right? When your x is 0, what is your f of 0? F of 0 is 0. So this is 0. In other words, they're telling us to find the derivative, so limit when x goes to 0 of f of x over x. Now our f of x is x squared sine 1 over x over x. We can cancel one of the x's. So we get x times sine 1 over x. Oh man. I lost my work. Cut. It is this. But you already seen the left page, right? Do you want me to rewrite again? You're okay. You're okay? So at the end, we got this is same as limit x is going to 0 of the simple function x sine 1 over x. Right? This is what we ended up getting after applying the definition. Now we don't know what's the limit here. So what we do, we go to the squeeze theorem. Squeeze theorem is telling us that if you know one function is lying between the two functions, and the two functions at the end and in the front have the same limit, then the middle function will have the exact same limit. This is the squeeze theorem. So how do you apply? Squeeze theorem. We start with sine 1 over x. We definitely know that sine 1 over x lies between which two numbers? -1 and +1. It's guaranteed, right? It doesn't matter what x is, it will always lie between -1 and +1. Now, if you multiply all the sides by x, we end up getting -x, x sine 1 over x, +x, right? And now let's apply the limit to all three. So we are applying limit here. Limit x is going to 0. So we get limit x is going to 0 of -x less than or equal limit x is going to 0 x times sine 1 over x, and limit x is going to 0 of +x. When you apply limit, you apply to all three, and then we see what is this limit. When x is going to 0, our limit here is 0. When x is going to 0, our limit is 0. So we know that our function, what you're looking for, lies between negative x, positive x, and they both have the same limit 0. So squeeze theorem is guaranteed. Squeeze theorem guaranteed that the middle function has the same limit. So this limit is going to 0. In other words, they are telling us to find derivative at 0, and we know derivative at 0 is same as limit x is going to 0 of this function, x sine 1 over x. And by squeeze theorem, we found that this limit is 0. That means our derivative at 0 is 0. But this will not be true if sine has a different function in the front. So here x squared makes sense. We have this limit. But if you have only x, then no, the limit is not 0. So in your homework, if you haven't done the homework yet, in your homework you'll see one of these examples. Definitely that homework doesn't have the answer 0, okay? So do your math and figure out what's the answer. Question? Go ahead. No, it depends on what function you're working with. For example, you can now apply this to tangent. Tangent definitely doesn't lie between -1 and +1, right? It doesn't have any boundary. It's tangent. So for tangent, you cannot use this squeeze theorem. So your function, if you know that your function has a boundary, an upper boundary and lower boundary, then you can use the squeeze theorem. Any other question?
Wait, how do we know that the limit at a certain point is equal to the derivative? Is that just like a fact?
This is the definition.
Oh.
Definition of the derivative. So in derivative, we use f prime of x. It means what is the limit for any x value. And if you know your x value, then you can use the second definition, which is the exact same thing. It just looks different, but the exact same thing. Any other question? So that was one interesting question. I was planning to give this question in the exam, but since we didn't go over this section, so I omitted that. Maybe I'll put in my second exam. It's interesting. Okay, the next one. What do you think is the answer? Did you find the answer? What is the option? A, B, C, or D? What do you think, Apollo? D? All three are correct. All three are true. The limit exists, it's continuous, and it's differentiable. Anybody found something is not right here? Like the answer is not D. Ellen? You think it's B. So B says only these two is true, that it's not differentiable. Ellen, what do you think? Andy? X minus 4, x squared. It does have a short term. But we don't know, right? Like we didn't graph it. It says, just find it. So if it did not use graph, that means you have to use the definition. Definition of continuity and definition of derivative, okay? So, limit exactly at 3. How can we find the limit exactly at 3? In order to find the limit exactly at 3, what do you have to look at? This was in your exam 1. Find the limit, find the exact limit. So if you want to find the exact limit for a piecewise function, how do you find the exact limit? See, this limit, this function has two sides, so you have to look at the left side and the right side. So they are telling us if this is 3, before 3, we have a function x minus 4. And after 3, we have x squared minus 10. And this is also inside the 3. So when x is 3, this is our function. And when x is smaller than 3, strictly smaller than 3, this is our first function. To find the exact limit, we have to see what's the left limit and what's the right limit. And do they give us the exact same y value? If they do, then the limit exists. And that's the limit. So I need to find what is the limit when x is going to 3 from the left side. So the left side of 3, what function we have? Which one? X minus 4. So we substitute the 3 because it doesn't have any problem. It's a straight polynomial. We get 3 minus 4, which is -1. Now what happens when you find right side limit? Limit x goes to 3 from the right side. So what function we have on the right side? X squared minus 10. So we substitute 3, we get 3 squared, which is 9 minus 10. So -1. We do have the same number, same y value. So what is the exact limit? Limit exactly at 3 of this function is -1. So A is correct. The limit does exist. And yeah, it does exist. Now we have to see continuous. Now in order to see continuous, if the limit exists, then it's automatically continuous, right? Continuity follows 3 rules. Sorry, my bad. What I said is totally wrong. Just because limit exists, it doesn't mean its function is continuous. Continuity has 3 conditions. Do you remember? Limit must exist. The left limit, the right limit, y value must exist. The limit must exist. And what's the third condition? Y value and limit, they have to be the same thing. So we found the limit is -1. We want to see what is the y value when x is 3. So when x is 3, our y value is lying inside the second function. So when x is 3, what is our f of 3? We substitute the second function, right? And we get -1. So y value does exist, it's -1. Limit does exist, it's -1. Limit and the y value are the exact same number. So yes, it is continuous because all 3 conditions satisfied. And now for differentiability, we need to look at the definition of the derivative. So derivative of this function when x is 3. Since we know our x value, so we are going to use the second definition. It says limit x is going to 3 f of x minus f of 3 divided by x minus 3. When you know your x value for the derivative, you use this. And when you don't know, you're finding the general derivative, you use the first derivative with the h. So limit h, not h, sorry, x is going to 3 of f of x. What is our f of 3? -1. So negative, negative turn into +1. And then x minus 3. So limit x goes to 3, f of x plus 1 over x minus 3. And then how can you find this limit? Any idea? But f of x has two portions. Why? But you didn't say you're approaching from left side or from right side. So when it doesn't mention left or right, it means you're approaching from both sides. And I give you the answer. What's the limit here? How do you find the limit here? Conjugate. You don't have to make your life harder. In order to find the exact limit, how do you find the exact limit? Left limit and right limit. Look at the limit from the left side. Look at the limit from the right side. So we do the same thing again twice. Limit x goes to 3 from the left side. When you use the left side, that means our f of x is the upper function. So it's x minus 4 plus the 1 over x minus 3. So we have x minus 3 over x minus 3. They both cancel out. So what's the limit? 1. We do the same thing. So this is 3 from the left. Limit x is going to 3 from the right side. And this time our function is x squared minus 10 plus 1 x minus 3. So we get x squared minus 9 over x minus 3. And then what happens? Difference of squares. X plus 3 over x minus 3 over x minus 3. So they cancel out. We get limit. I don't have space. Oh, I have space here. We get the limit x is going to 3 from the right side of x plus 3. Right? Because we cancel the minus 3 from the bottom. So this time we have no problem. We substitute and we get 3 plus 3, which is 9. Sorry, 6. Man. Thank you. So our left limit is 1, right limit is 9. So what is this limit? Doesn't exist. So number 3, the option 3 is wrong. So only A and B correct, 3 is wrong. And if you don't want to do all this work, then you can just graph them. Before 3, so we have 1, 2, 3. Before 3, we have a linear function. What is a linear function? X minus 4. So minus 4. It's when x is 0, -4. something like this. When x is 0, y is -4. Yeah. And then after 3, you have a function x squared minus 10. So x squared minus 10 is somewhere, x squared minus 10 is, so 10 is here. And then we have something like this. I could be wrong, okay? The idea is this thing. Here, it should be something like this. So here we have a straight line, and then it's kind of, it has a sharp connection in the middle. My graph looks bad. Let me use that. I can use Desmond's. So we have x minus 4, and we have x squared minus 10. So x squared minus 10. Okay, so before 3, we have this, and after 3, we have that. So can I write it here? Oh. So before 3, this is the graph. And after 3, this is the graph. Here, we don't have a smooth transition from one graph to another. It's kind of a sharp. So 1 is going here, and then suddenly it goes there. So it's a sharp turn. Why do you care about sharp turn? Derivative doesn't exist at the sharp turn. Okay. If you know your graph, and if you know that derivative doesn't exist at sharp turn, you can simply use that theory, or you can use the way I did. Find the derivative, check the continuity, and check the y value and see which one makes sense. Question?
Okay, I get how you did all that, but at the end, like, how would you notate that it's not differentiable, but there is a limit? Because it's both like when x approaches 3, and one of them you said it's -1, and then the other.
The limit exists for the function.
Okay.
But when you look at the derivative has a different function. So this is the derivative function. And you're taking the limit of the derivative function.
I got it.
So the limit of the derivative function tells you about differentiability. But limit on the original function tells you about continuity. Clear? Now the last one is the interesting question. They gave us the derivative when x is 5. What is that function? What's the answer? A, B, C, D, E. Which one makes sense? Don't be afraid. Just tell me anything. What do you think? C. Why do you think it's C? How did you figure that out? What was your method?
So whenever we said the plugin of X, then that's the
Exactly. That's the trick I use. So here, if you observe, they're using the H formula. H means the formal definition. So the formal definition says f of x plus h minus f of x over h. Now, whatever we have here, that's your function. So whatever we have here, this is our function, but they're telling us our x is 5. So this is f of 5, 1 over square root of 5. So if you want to know what is f of x, you just replace your 5 with the x. That's it. You don't need to do any math. It's simple observation. A little bit smaller. Question. Yeah. Now rate of change. So velocity is the speed of something in a given direction. So it's like distance over time. Average velocity is the rate at which an object changes its position from one place to another. If the rate of it's the rate of change of an object's position with respect to a time frame. So average velocity is the slope, which is average rate of change. And it's also the slope of the secant line. On the other hand, if you look at instantaneous rate of change, is the slope of the tangent line. So slope of the tangent line is the slope at a point, right? Same thing, instantaneous, meaning exactly at that moment, what was your velocity? Or what is your rate of change? So in that velocity, what was your rate of change? So that instantaneous tell us slope of the tangent line, while average tells us the slope of the secant line, which is two different points. So velocity or instantaneous velocity is simply the derivative of the displacement. Displacement means you're moving from one position to another position. And I already told you that before. If you have a position function, to find the velocity, you just take its derivative, because derivative is the velocity. And acceleration. Acceleration is the derivative of your instantaneous rate of change, which is velocity, derivative of the derivative, which is the second derivative. Now, one example. Find the average rate of change of the function. Now, average rate of change and instantaneous rate of change, they are not same, right? Average rate of change, look at the 2 points and take the average of the change, which is the slope of the secant line, which is the slope of the normal line. I mean, not normal, sorry. I shouldn't say normal. Which is the slope of a regular line, slope of any regular line. So what is the slope of any regular line? We can rewrite this in a fancier way. Let's say if you have 2 points, if this is your x1, y1, sorry, if this is your x1 and x2, this is same as f of x2 minus f of x1 divided by x2 minus x1, right? y2 is the y value respect to the x value x2. And y1 is the y value for the x value x1. In other words, they're telling us find the y value twice and plug in here. So let me do it on the side. When x is 1, x1 is 1, our y1, which is f of x1, is negative cube 70 plus 1. So negative 1 plus 7 plus 1, the answer is 7. For x1 equals 1, our y1 is 7. When our x2 is 4, we are looking for y2, which is simply f of x2. Tell me how much you have. So all of this becomes 4, and the final answer is what? Negative 64, right? Plus 28 plus 1. So what is our y value? Negative 64, positive 29. Come on, guys, it's a simple math. Negative 35. Okay, So we found the two y values. That means you can find the average rate of change. It's negative 35 minus 7 divided by 4 minus 1. Negative 35 minus 7. How much we have? Raka on our laptop. Please close it. What is negative 35 minus 7? How much is it? 42. Can we divide 42 by 3? How much? 14. So basically, they are telling us that we are going down at 14. Do they have any number? No. At 14 minutes per second, something like that. So slope is negative 14. That's the second line. Second line gives us average. Anytime you see average rate of change, it's the slope of the second line. That means you're not finding the derivative. If they ask, find the instantaneous rate of change, they need to find the derivative, which we are going to do later in 2.8 or something, I don't remember, or 2.7. Any question? That's all from 2.1. No question? Then now we are going to 2.2, which is a fun section. It's fun because we are going to work with, can I change my word? I guess done. Logan, are you okay? Can I change it? Okay. So how derivative works as a function? That's the idea here. How can you sketch a graph of derivative based on the function? So as we have seen, the derivative of a function at a given point gives us the rate of change of the slope of the tangent line. If we differentiate a position function at a given time, we obtain the velocity at the time, which is the exact same thing. It seems reasonable to conclude that knowing the derivative of the function at every point would produce valuable information about the behavior of the function. So if you know your derivative or slope at every point of the function, that means you have some idea how the function is going or how it's flowing from one point to another point. The derivative function gives us the derivative of a function at each point in the domain of the original function for which the derivative is defined. It means we can find the derivative anywhere where the function is defined. If the function is not defined, we cannot find the derivative. A function f of x is said to be differentiable at a point A if derivative at that point exists. So if the derivative exists, it's differentiable. If the derivative doesn't exist, it's not differentiable. This is what we say. More generally, a function is said to be differentiable on an interval S if it's differentiable at every point on S. So let's say you have a set from A to B. If the derivative exists everywhere between A and B, not including A and B, then we say, well, this function is differentiable from A to B. We don't look at the derivative at the end. Okay? We look at the derivative between 2 points, within the interval. Now, where the function has a derivative or where we have a tangent line. A function has a tangent line or it's differentiable when we have a smooth, continuous, no sharp turn. Okay, so you have a smooth function on an interval, a derivative exists everywhere in the interval. Then when the derivative doesn't exist, it doesn't exist at 4 places. At a sharp corner. For example, something like absolute value function. it doesn't exist. Derivative doesn't exist here in the sharp corner. Or let's say you're going here and suddenly, I didn't mean that. Let's say you're going here and then you suddenly take a sharp turn. The derivative doesn't exist here. It exists before the sharp turn, after the sharp turn, but exactly the sharp turn derivative doesn't exist. It also doesn't exist when you have a hole. For example, let's say you have a smooth curve, but then somewhere you have a hole. Derivative doesn't exist at the hole. And then break and jump. Let's say you have a smooth part here and then a smooth part there. The derivative doesn't exist here. You can see jump. It has to be continuous, must be continuous. But there is one thing. This is a continuous function, but still derivative doesn't exist. So derivative and continuity, they go hand in hand. In order to be differentiable, the condition is it must be continuous. But just because it's continuous, it doesn't mean it's derivative. So it doesn't go two way, it goes only one way. If it has a derivative, that means it must be continuous. But just because it's a continuous, it doesn't mean it has a derivative because of the sharp corner. And lastly, vertical asymptote. Let's say you have a function like this. One is going up and one is going down. Derivative doesn't exist at the vertical asymptote. Now some other example. Where this graph doesn't have a derivative. Few of them are very obvious, but at least one is not so obvious. Go ahead, Apollo. 1. Why derivative doesn't exist here? Sharp corner. And then the second one, we have a hole, so it doesn't exist. X equals 3. Then we have a sudden jump, so at 5, it doesn't have a derivative. So answer is x equals 1, 3, 5. Any questions so far? Okay, what do you think about the next one? At which point the function is continuous, but not differentiable. Ziad, would you like to answer this question? It's continuous, but not differentiable. Perfect. Here we have a sudden turn. One side is going down, and then suddenly it's took a sharp turn to go up. So yep, the answer is x equals 3. Any question on this one? No. Think about this one. Continuous but not differentiable. Point A. Perfect. So is it clear that just because it's continuous, it doesn't mean we have a derivative? So the example we did before, the piecewise function, it was continuous, right, at 3, but it wasn't differentiable because it had a sharp turn. And we proved it using the definition of the derivative instead of looking at the graph. Now state all the x values where the derivative doesn't exist. Let's see. Go ahead, Apollo. So at x0, y doesn't exist? Vertical asymptote. And x equals 3, y doesn't exist? Sharp corner. Easy, right? So I'm planning to give a few of these in the exam for you to have fun in the exam. So enjoy. The next one. Why derivative doesn't exist? Andy, would you like to try this one? X equals -1 means here. What's the reason? Break or jump. And x equals 2, y, sharp corner. Cool, right? All of these are easy questions. And now some fun things. What the first derivative tells us about the function. So if you know your first derivative or picture of the first derivative, can you identify its, can you assume or can you guess its original function? Or vice versa. If you know your function, can you figure out its derivative, function of a derivative? So it says, since the derivative is the slope, so from linear function, we know that if a slope is positive, the line is increasing. If the slope is negative, the line is decreasing. We know that from algebra. Now, based on that, we can say when our derivative is positive, the function is increasing. When our derivative is negative, our function is decreasing. And when the derivative is 0, the function has a bump because our slope is 0 when we have a horizontal tangent line. And horizontal tangent line happens only when you have a turning point. Either you have an upward or downward bump. So at every point where we have a change, we call them critical points. Change means when the derivative is 0. So if you ever forget this, connect this information with algebra. Positive slope means you're going up, it's increasing function. Same thing. If you have a positive derivative, means your function is increasing. If you have a negative derivative, means function is decreasing. And positive, negative, if you're looking at from a graph point of view, this positive and negative means, positive means your graph, f of f prime graph lies above the x-axis. This is what positive means. And here it means f prime graph lies below the x-axis. And derivative is 0, it means f prime is crossing the x-axis. It's like normal thing. If you have x and y, so positive means your y value is on the top portion of the x-axis. Negative means your y value is lying below the y-axis. And 0 means either you're crossing here or there somewhere. So if you're looking at a graph, this is what it means for derivative. If the derivative is lying above the x-axis, the original function is increasing. If the portion of the graph is lying below the x-axis, it means the original function is decreasing. And when the derivative crossing the x-axis, at those points, we have a bump in our original function. And we also have second derivative. How does second derivative help us? What second derivative tells us? Second derivative is the derivative of the first derivative. So it's the slope of the first derivative. So when the second derivative is positive, it means the derivative function is increasing. When the second derivative is negative, it means the derivative function is decreasing. And when the second derivative is 0, it means our derivative, the first derivative, has a bump in its function, in its graph. But then how can you connect the second derivative with the original function? I have it on the next slide, but let me tell you here. First derivative positive, it means the original function, f of x, has a concave up portion. In that portion, the graph is concave upward. When the second derivative is negative, it means your graph has a concave down shape, concave downward. And when the second derivative is 0, it means you are changing your position from either increasing to decreasing or decreasing to increasing. For example, either you have this shape or you have decreasing to increasing shape. So you have increasing upward before, downward after. So this is your second derivative 0, and here this is second derivative is 0. So when you change your position from concave up to concave down or concave down to concave up, at that time we have the second derivative 0. When the second derivative is positive, means the original graph is concave upward, and when the second derivative is negative, the original graph is concave downward. And when the derivative, second derivative is 0, they have a special name. We call them inflection point. So the first derivative gives us critical point. The second derivative gives us inflection point. For now, we're not going to use the second derivative. We are just going to use the first derivative. But I'm giving you the information before. So when you see anything with the second derivative, you have the knowledge what they mean by that. And I put together all this information in one table. F prime is positive, means the graph is lying above the x-axis. It tells us that our original function is increasing. F prime is negative, means the graph is lying below the x-axis. It means the original function is decreasing. F prime is 0, means it's crossing the x-axis. It means we have a bump into the function while we have a local maximum or minimum, and we call them critical points. Then when second derivative is positive, it means our first derivative is increasing, so original function has a concave up. When the second derivative is negative, that means first derivative is decreasing, so original function is concave downward. When the second derivative is 0, that means this time the first derivative has a bump, and it means we have inflection point in the original function, while we are changing our direction from concave up to concave down or other way around, vice versa. Clear? Question? None? Now let's do some example. Sketch the graph of the derivative of the following parabola. They gave us the original function. Can you sketch the graph of its parabola, the graph of its derivative? So I give you all the information. here. This is the information about the original graph. So they give you the original graph. They're asking us that based on the original graph, can you tell us about the first derivative? Can you sketch a graph of the first derivative? Interesting question. So can you connect your knowledge with some application? This is the original f. Here. They're asking, what is the shape of its derivative function? So when it's 4, it will go and it's decreasing. Is it? Anyone disagrees? Apollo. Increasing. Okay. So Logan, why your graph is decreasing? Parabola is negative, it flips. Okay. Can you connect that information with the parabola? Like it says increasing, decreasing, and then flying above or below x-axis. Can you connect the information? Instead of looking at algebraically, can you look at graphically? It's getting increasingly smaller. So it's increasingly smaller. Why the derivative is going down though? And also it's not only increasing, it's first increasing and then decreasing, right? So why graphically, not algebraically? Algebraically, we can see that. Graphically, why this graph has this derivative? Yeah. It's concave down. That tells us about the second derivative is negative. What does it tell us about the first derivative? This is the first derivative. Decreasing. Right, so it's concave down. That means second derivative is negative, so the line is decreasing. And how do you know it's going to the axial wall? So this is the story. When the original graph has a turning point, a bump, we have a horizontal tangent line. Come on. Right? And horizontal tangent line has a slope 0. It means our derivative is 0. Derivative is 0 means crossing the x-axis. So when x is 4, our derivative is crossing the x-axis, so it has to cross the x-axis. And then, like they mentioned, concave down, so we have the second derivative negative. Second derivative negative tells us that our with the first derivative has to be a decreasing function, not increasing function. So it's not increasing, it's a decreasing function. And also, see, from this point to this point, the function is increasing. Function is increasing means the derivative is lying above the axis. That's why before -4, our graph has to lie above the x-axis. And then from 4, the function is lying down, so decreasing. It means that derivative is below the x-axis. Yeah, it's below the x-axis. Question? How about the other way around? If this is the derivative, what is the original function? You want to try? Straight line? Are you sure? Now this is a derivative. So previously this was the original function, this is the derivative. Now you are going one more here. What is the original function that gives you the derivative parabola? It's not a straight line. Straight line is a derivative, but I am, in other words, I'm talking about the entire derivative.
So I thought that was the original.
Now this is the derivative. Gives us the original function. You're going backward.
The cubic.
It will be a cubic. Give me more information.
Two would be very flat, horizontal. And then there it would going from
So we have 0, we have 2, we have 5. We put 2 a little bit to the left. So how you're moving from left to the right, from before 0 to 0, how you're going?
up left,
So you're going down?
yeah, and then just follow that too.
So it will have a bump like this.
Yeah,
And then are you going up or are you going down from there? Down. And then we are crossing through. 2. And then what happened? Oh, this is actually, we need 4. This is a 4.
only there would have to go back through.
It has to go back up. Does it make sense? No. It's a derivative. This portion is lying above the x-axis. Actually, you're wrong. Lying above the x-axis means original function is increasing, right? So this portion here is positive derivative. Positive derivative means your function is increasing. But the one I draw, the function is decreasing. So maybe something like this. Before 0, our function is increasing. So I don't know from where, from negative infinity, the function is increasing. And then we are crossing the x-axis through 0. So this is 0. I can draw it. So let me draw here. So we have, let me reopen this file. Come. So we have crossing the x-axis twice. Once it at 0 and once it at 4. We can see that clearly, right? Point the derivative is 0. Sorry, not that. When the derivative is 0, we have a bump. So we are increasing until we have a bump. When x is 0. It could be above x-axis or below x-axis, I don't know. I'm just estimating. I'm just guessing, okay? So the blue portion is telling us that we have an increasing function until 0. And then we have the yellow portion. Between 0 to 4, the derivative is negative. What does that mean? When the derivative is negative, what happens to the original function? Decreasing, right? So we have the next portion, the graph is decreasing. And this one, our derivative is 0. That means we have a turning point, inflection. So it's decreasing and then suddenly it's increasing. No, decreasing, increasing, something like this. It's a turning point from concave upward to concave downward, something like that. So concave down to concave up. Why is this happening? It's happening at 2. So let me change my 4. So this is the bottom. Derivative is negative, means the original function is decreasing. And then at 4, we have a turning point. So this is 2. So this is 4, somewhere here. It looks so weird. At 4, we have a bump. And then the graph is increasing forever. It definitely looks so weird. Above the x-axis means our function is increasing. Then we are crossing through the x-axis, means we have a horizontal tangent line. Then we are lying below the x-axis, means the original function is decreasing from 0 to 4. But then why are we increasing here? It's decreasing from 0 to 4. And at 4, we have a horizontal tangent line. And then we're increasing forever. So this is decreasing. And then we have increasing. Is this portion? Does it make sense? It does look like a cubic graph. It has to be a cubic graph, right? Because the derivative of a cubic graph, if f of x is x cubed, its derivative is 3x squared, which is the parabola. Go ahead, Logan. At point 2, it's turning. So see, from here to here, it's concave downward. And then from here to here, it's concave upward. So at 2, it's turning its position from one position to another position. That's why you have inflection point at 2. And this is the accurate picture. Oh, I don't have the accurate picture. Oh man. Try this one. It has more problem. So this time they actually gave us the original function. So it should be easier. The original function is given, draw its parabola, draw its derivative. I thought this would be fun, but for some reason you're not enjoying, right? They actually highlighted the main point, A, B, C. So this is the original graph. Draw its derivative graph. And every time this graph has a horizontal tangent line, it means you're crossing the x-axis for the derivative function. Ready? So you're looking at three things. Every time they have a horizontal tangent line, we are crossing the x-axis. So you're crossing the x-axis through A, through B, and through C. These are the three places we are crossing the x-axis, right? Now, what is happening before A? Before A, we have this portion. Is it increasing or decreasing? So decreasing means the derivative. Is it lying above the x-axis or below the x-axis? Below, right? Somewhere here. And then we have to go through the A to cross. So we are crossing. Clear? Before A, what is happening? Is it clear? Then we go to between A and B. What is happening in A and B? The original function is increasing, right? So what is happening to the derivative? It's lying above the x-axis. And then through B, we have to cross it again. That means some point you have to come down. So from A to B, that portion is lying above the x-axis, and we have a curve somewhere because we have to go through B somehow. Okay? Who is lost so far? Go ahead, Apollo, tell me. So the rule is this. When F increases, let me use the symbol. When F increases, the derivative is lying above the x-axis. When F is decreasing, the derivative is lying below the x-axis. When we have a bump, either this way or that way, when we have horizontal tangent line, we are crossing the x-axis. So definitely we are crossing the x-axis here because we have horizontal tangent. We are crossing the x-axis here because we have horizontal tangent. So there are three places we must cross the x-axis, A, B, and C. Now before A, the graph is going down, right? From infinity to going down. So when the graph is going down, our derivative is to lie below the x-axis. So somewhere below the x-axis, we have our derivative. And then we are crossing through A because we have horizontal tangent line. Now between this horizontal tangent line and that horizontal tangent line, our graph is going up. So if it's increasing, F increasing means our derivative is lying above the x-axis. Just lying above the x-axis, but it's not increasing forever because we have to go through B to cross the x-axis. That means it's above, okay, but somewhere it's increasing, then it's going down. So it's crossing the x-axis through B. So it crosses the x-axis through B. And then what is happening from B to C? The original function is increasing or decreasing what? Decreasing. So it's going down again. So that portion from B to C has to be below the x-axis, but then we have to go to C again because we have a horizontal tangent line. That means we have to go up somewhere so that we can cross through C. And then lastly, after C, what is happening to the original function? Increasing. So that portion is lying above the x-axis. So this is the graph. It's not exact by sketch. So now who is confused? Still confused? Anybody? Before you go, there is one more question. Actually, not one more, a few more. Let's start with something fun. The right one. There are 4 graphs, A, B, C, D. Which one is the original graph? Then its derivative, then its derivative, then its derivative. Can you figure that out? Pink is A, blue is B, green is C, black is D. Among all these 4, which one is the original one? What do you think, Sanzim?
Yes, but
Uh-huh.
with DBF, F prime is C, double F prime is D, and triple F prime is that.
What do you think, guys? Any objection on this?
I kind of want to switch this F prime and F prime.
So you want to write, this is the third derivative and this is the first derivative, right? C and A.
No. I wanted to switch his B and C.
B and C, oh.
He's the first derivative and C is the second. Like, I don't have to solve it.
So B is the first derivative and C is the second derivative. And what is your F? D?
And yeah, the rest is the same.
Okay, so F is some type of add function, right? So let's say this is x to the 5. Because I'll say the blue one is x cubed. The blue one looks like x cubed, right? It's going to the 0 straight. So blue one is x cubed. Let's say this is x to the 5. Now, if f is x to the 5, what is its derivative? 5x to the 4. Means we have an odd function, even function. So which one is true? C or B? Which one is even? C. So B cannot be its derivative. Derivative in odd has to be even. And derivative even has to be an odd function, right? So if f is D, C has to be its derivative. And then if f prime is x to the 4, what is its prime? What is its derivative? 20x cubed, right? So see, blue one, it's a cubic function, 20x cubed. So the blue one is the second derivative. And if blue one is the second derivative, what's the third derivative? 60x squared. Look at the pink one. It's a square graph. It doesn't matter how many, what's the thingy, coefficient.
The way I got it was that I was looking at the inside. So like the inside, I noticed that the pink one was like concave and up, right? So that means I knew like the previous function would have to be negative, then positive, and from there I just put it up.
Good. So you went from inside to outside, and I actually looked at outside to inside. But we both got the same result. Who is confused? Anyone? So make an observation. Every even function has an odd function derivative. And for every odd function, we have an even function derivative. So if you can have this observation, I think you'll understand how derivative works. Okay, so for today, we'll stop here. On Wednesday, we're going to have in on-person class And we are going to do a few more examples of this. Okay. From original function, make your derivative, and then you are going to go implicit differentiation. Okay. On Wednesday, we are going to do implicit differentiation and more of these fun questions, which is supposed to be fun, but you guys didn't enjoy. I hope you will enjoy next class. Oh, and many of you didn't do homework. Okay. Make sure you complete all the homework, guys, please.